These are your Earth Science notes for Unit 2, the history of Earth. So we're going to start with Earth's formation. So Earth first formed 4.6 billion years ago. Keep in mind that this is about 9.2 billion years after the Big Bang. So the Big Bang was about 13.6 billion years ago, 13.7 billion years. Earth didn't form till quite a bit after the Big Bang, about 4.6 billion years ago. So there was mass and dust rotating around the sun. So all those different elements and that dust kind of rotating around the sun began the formation of early Earth. Gravity kind of pulled them together. First Earth was molten magma oceans with no atmosphere and no oceans. We call it a magma ocean because it was literally just like flowing melted rock everywhere. As the Earth cooled, volcanoes started to form, right? The crust on the top cooled, magma was still coming out like a volcano does. And as those volcanoes erupted, it released gases, and those gases formed the early atmosphere of Earth. That early atmosphere contained gases like ammonia, methane, water vapor, and carbon dioxide, and only very small trace amounts of oxygen, not enough oxygen to support any life yet. So you can see this is just kind of like an artist's depiction of what that early Earth would have looked like. So lots of meteorites bombarding Earth, these magma everywhere, very cloudy, kind of toxic atmosphere. As the atmosphere began to form, then we had clouds forming from the water vapor, condensing in the atmosphere, and then rain began to fall. So that rain plus comets and asteroids that were striking Earth created what are the early oceans. So as those comets and asteroids struck, they kind of, thinned out the crust, kind of dug it down to create an ocean that was filled with the rain from the clouds in the atmosphere. The early atmosphere and oceans would be toxic for today's life because there was not an abundance of oxygen that we need. All right, so let's talk about the Earth's layers. So as that early molten Earth cooled, the materials that made up Earth started to separate according to their density. So more dense elements, things like iron, fell to the center of the Earth to create the core, and less dense elements like aluminum and silicon created the crust on the outside. So the layers were formed because of the different density of materials. So starting from the center of the Earth and working outward, in the very center we have the core. The core is divided into two sections. We have an inner core, which is the very, very center of the Earth. And the layer outside of that is the outer core. When we're talking about the inner core, that is a solid, right? It's a solid inner core. It's about 6,400 to 5,100 kilometers below the surface. So that's how far down we would have to go from the surface that we're on. The core is very, very hot, around 9,800 degrees Fahrenheit. And it is mostly made of those dense metals like iron and nickel. So they are so compressed in the center that it actually forms a solid. The outer core, so the layer above that, is liquid. So it's about 5,100 to 2,800 kilometers below the surface. The radioactive decay is going to rotate the material. So as these different elements decay, that liquid is actually going to rotate. It's what's going to keep everything in a liquid state. Again, it's mostly iron and nickel, but it does have a lot of those radioactive elements, like we mentioned, that's going to decay and cause it to rotate. That rotation of that outer core is what creates the magnetic field that we have here on Earth. Above the core, we have the mantle. The mantle is around 3,000 miles thick. It is approximately 100 to 400 kilometers below the surface. And so that's how far down we'd have to dig to reach the mantle, but it's very thick. It's the Earth's thickest layer. And it again circulates because it is liquid, but it circulates much slower than the outer core. Right? Slower than this should say the outer core. The outer cores are going to rotate much faster to create that magnetic field. The mantle moves as well, but at a much slower rate. The layers are going to get cooler as we get closer to the surface. So this inner core is the hottest. As we get closer to the surface, to the crust, the layers are going to cool. So this mantle part here is made of iron as well as some lighter elements like magnesium and silicon, which is what causes it to be above the core, right? That density is what's going to separate it. The upper part of the mantle is known as the asthenosphere. Asthenosphere is what it's called. Upper part of the mantle. It is approximately 100 to 200 kilometers below the surface, depending on where we're looking. This is the point where the rock from the crust is melting. So it's made of partially melted rock. We call this kind of a plastic layer. It's not totally liquid. It's not totally solid. It's that meeting place of where the melted mantle and the solid crust meet, right? So it's kind of a mix of the two. This asthenosphere is the layer that's responsible for moving Earth's tectonic plates that we will be talking about shortly. Above the asthenosphere, we have the crust. The crust is a very thin, rigid layer. It's solid. It ranges from 5 to 70 kilometers thick, depending on whether it's below an ocean or below mountains. So ocean crust is generally thinner, and continental crust, which we think of as land and mountains, is generally going to be the thicker crust. You can see that here, right? Here we have very thin crust. The crust gets very thick over here where there's mountains and hills. This crust is divided into tectonic plates that kind of float and move on top of the asthenosphere. So let's talk about how those plates move and change. So there is this theory called continental drift that talks about Pangea. So the theory of continental drift tells us that Earth's continents were once joined as a single landmass. We call that landmass Pangea. Pangea just means all the Earth. So all of the continents at one point were connected into this giant supercontinent. Pangea broke apart approximately 200 million years ago. Since breaking apart, the continents have been continuing to drift to their current positions. So we have a couple lines of evidence that tell us that continental drift occurred. First is the fit of the coastlines. So if we look at the coastline of South America and of Africa, it looks like they fit together just like a puzzle would, right? We can kind of fit those two continents together. That's a piece of evidence showing that at one point they were joined together. Another piece of evidence are similar rock formations. So rocks in areas that were once joined together have the same age and the same type of structure. So in the US, we have this mountain range called the Appalachian Mountains, which is kind of in the east and south part of the US. And at one point, the US, North America, was connected to Africa and Europe. And there are actually mountain ranges in the northern part of Africa and in Europe and going across Great Britain and into Scandinavia. And all of these mountains have very similar ages. They have the same types of structures, same layers, same similar ages, because at one point it made one giant mountain range. Third piece of evidence are fossils. Fossils of land animals and plants can be found on continents that are now very far apart from each other, suggesting at one point the land was joined. For example, this plant, this green one, we find fossils of that plant across South America, Africa, India, Antarctica even, and Australia. So even though those continents were once really far apart, this tells us at one point they were joined together because this plant was able to grow at the same time through that wide region. Same with this Signathus is what it's called in South America and Africa, showing that they were once joined together. And then the fourth piece of evidence for continental drift is climate changes. So layers of coal are now found in cooler regions. Coal is made by what was once kind of tropical areas. So if we look in Europe, for example, and in North America, we don't have a tropical climate here in North America, but at one point it was connected and did have a tropical climate, which formed that coal underground. We can also find glacial deposits from this large glacier. We can find remnants of that glacier on Africa, India, and South America, even though now those places are in tropical regions. At one point, they had a glacier that covered them. In the middle of the Atlantic Ocean, we have something called the Mid-Atlantic Ridge, which is basically an underwater mountain range. That is a location where two tectonic plates are diverging or pulling apart from each other. The magma from the asthenosphere and the mantle is going to rise up and create new ocean floor. So essentially, those two plates are moving apart from each other, and magma is coming up in that crack and forming new crust. So you can see that happening here. So magma is rising to fill what we call a rift valley, and this creates that mid-ocean ridge. That's formed as the lava cools and forms new rock and new crust. So the very center of that mid-ocean ridge is the youngest crust. And as those plates move apart, the further we are from that ridge, the older the crust is, right? So we have constant new land in the center. And as we move further out, the land gets older. Magma is too hot to have any sort of magnetic qualities, but as that magma cools, when it's forming that new land in that mid-Atlantic ridge, its magnetic properties return. So it gets its magnetic properties back as it cools. Earth's magnetic poles switch places every about 100,000 years or so and are going to align the particles in that rock in the opposite direction. So this is going to create what we call stripes in the seafloor. These stripes just represent the polarity of the magnet. So you can see here is oriented in one direction, then the white, it switches. And then the next color, it switches again. And then white, it switches, right? So if we measure the magnetic polarity on the ocean floor, we find these stripes from where the crust is constantly being formed. So this shows us over time that it is moving apart and forming new land in the center. So where is Earth's oldest crust found? We know the newest crust is formed at the Mid-Atlantic Ridge. The oldest crust is continental crust. Continental crust in general is much older than oceanic crust. And there's a particular place in Jack Hills, Australia, that was remnants from the lava ocean or that magma ocean that we talked about before that used to cover Earth about 4.4 billion years ago. We still have remnants of that in Jack Hills, Australia. So that is the Earth's oldest crust. All right, let's talk a little bit about geologic time. So geologic time is broken up into units of time based on changes in the Earth's surface, climate, and types of organisms. Instead of thinking it as just billions of years, we kind of divide it up into sections so it's easier to recognize the different changes. So these are the 4 different units of time. We have eon, era, period, and an epoch. The biggest unit is an eon. So there are only a few eons in Earth's history. And each eon is going to have several eras. Each era has several periods, and each period has several epochs. So epochs are the smallest unit. So most of Earth's history is what we call Precambrian time. It started about 4.6 billion years ago. Right when Earth began to form was the beginning of Precambrian time, up until about 542 million years ago. So about 90% of Earth's existence is what we call Precambrian time. This is before the majority of life existed. It's before we had plants. It's while all of the atmospheric changes are still happening on Earth. That's all called Precambrian time. So let's talk about what the more recent times were like in Earth's history. So we had the Paleozoic era, which is from 542 to about 251 MYA. MYA stands for millions of years ago. During the Paleozoic era, that's when we really had a big increase in plant and animal diversity. So a lot of different types of plants and animals evolved around this time. This is the first time that we see vertebrates, which are animals that have a backbone. Life on land began because this is when the atmosphere started to develop a more oxygen-rich environment, which allowed for plants and animals to move onto land out of the water. And this is when Pangea was first created, right? So we're talking about when all the land masses were connected together. Then we have the Mesozoic era. Mesozoic era is from 251 to 65.5 million years ago. And this era is divided into 3 different periods, which you probably have heard of: the Triassic, Jurassic, and Cretaceous periods. This is what is known as the age of the reptiles, or the age of the dinosaurs. But we did also get the first mammals and birds. So prior to this was pretty much just reptiles and amphibians and fish. First mammals kind of came about in the Cretaceous period. And this is also when Pangea is beginning to break apart. So those continents are beginning to drift apart from each other. We have the Cenozoic era. We are currently in the Cenozoic era. It was from 65.5 million years ago to present day, and it is divided into the Tertiary and Quaternary periods. We're currently in the Quaternary period. We call this the age of mammals. So we had a large diversity of mammals evolve around this time. This is also when the first humans appeared on Earth. So let's look at where we are present day. Our eon, remember eon is the largest unit. We are in the Phanerozoic eon. The Phanerozoic eon is very, very long. It includes all the way back to dinosaur times, right? The eon is very big. That eon is divided into several eras. Our era is called the Cenozoic era. Before the Cenozoic was the Mesozoic, right? But we are in the Cenozoic era. That era is divided into 3 different periods. So we are currently in the Quaternary period. We also have the Neogene and Paleogene periods that are also in the Cenozoic era. And then each of those periods is divided further into different epochs. So we are currently in the Holocene epoch. Before the Holocene epoch was the Pleistocene epoch, which was about 11,000, so 11,800 Ka, which means 1,000 years ago. All right, so how do we know how old everything is? That has to do with relative and absolute dating. So there's 2 different methods we can use to date the Earth. Relative dating is going to compare the age of something to other things around it, right? So we're going to use words like younger or older. This rock is older than this rock, or this fossil is younger than this fossil. That's relative dating. Absolute dating is going to give us an actual age in numbers. So that's going to tell us, like, this fossil is 200 million years old, for example. For relative dating, rocks in Earth's crust are going to form layers. The older layers will be at the bottom. The younger layers are going to be at the top. So fossils found in different layers can be dated based on which layer they are found. We know older fossils found in lower layers are older than fossils found in top layers that are younger. Again, relative dating, not actual ages, just relative, older, younger than each other. So let's say we look for fossils in 2 completely different areas. For example, this is Montana and this is Texas. If we find the same fossil in 2 different locations in the same kind of rock, we can assume that those layers are about the same age, right? So let's say we find this is the 2nd layer in Montana, but it's the 3rd layer in Texas. We find the same fossil there. We're going to assume that those are about the same age. Right? Same with these 2 layers, right? We're going to assume they're about the same age. That gives us an approximate age for everything. Again, relative dating, older, younger than other things around it. Now that's different from absolute dating. Absolute dating is going to determine the actual age in numbers of an object using years, and we're going to use half-life to determine the number of years. So half-life is based on this idea of radioactive decay. So radioactive elements like uranium, carbon-14 are going to decay at a very predictable rate. By measuring the amount of decay of the element, it allows us to calculate the absolute age. So we can look and see how much of that element has decayed away, how much of the element is left, and use that to calculate the age of something. So the half-life is the time needed for 1/2 of a radioactive sample to decay into its daughter element. Okay, so for example, at the very beginning, We call that time zero, when no decay has happened. We have 100% of the parent isotope. In this case, we have 16 milligrams of the parent isotope. The half-life of this isotope is 10,000 years. In 10,000 years, half of that parent isotope is still there, but half of it has decayed into a different element called the daughter isotope. So half of 16 is 8. So 8 of it is the parent isotope, and 8 of it is the daughter isotope after one half-life, right, after 10,000 years. After another half-life, so 2 half-lives have passed, 20,000 years have passed, half of what is left of the parent is going to decay. So we had 8 milligrams, half of it is going to decay, so we only have 4 milligrams of the parent left. And we don't just have 8 milligrams of the daughter, we have 8 milligrams plus the 4 that also decayed, so 12 milligrams total. And this pattern is going to continue until there is none of the parent left. So by measuring the amount of that parent isotope, we can determine how many half-lives have passed. The number of half-lives is going to tell us the number of years so that we know how old something is. If I find there are only 4 milligrams, then I know it's been 2 half-lives, which is 20,000 years old. So you may see graphs like this showing the parent and daughter isotopes. Half-life 0, so number of half-lives is on the X. Half-life 0 represents 100% of that parent and 0% of the daughter, right? Nothing has decayed yet, so we have 100% parent, 0% daughter. After one half-life, half of the parent has decayed and turned into the daughter. So we have equal amounts of the parent and daughter isotope after one half-life. After 2 half-lives, this 50% of the parent is going to get cut in half again, down to 25%. And the other 25% is going to be added to the daughter, so that goes up to 75%. So the amount of the daughter is always going to increase. The amount of the parent element is always going to decrease. So here's a table representing that data. So for this element, the half-life is 150 days. So at 0 half-lives, time 0, so no days have passed, we have 64 atoms of the parent and 0 atoms of the daughter. After one half-life, that means 150 days have passed. Half of that parent is going to decay. So half of 64 is 32. Well, where did the other half go? The other half turned into the daughter. So now we have 32 atoms of the daughter element. After a second half-life, that means 150 more days, so 300 days total have passed. Half is going to decay again. So we no longer have 32 atoms. Now we have 16 atoms. What happened to the other 16? They turned into the daughter. So 32 plus 16 is 48. So notice the daughter is always increasing. The parent is always decreasing. Using this data, it may ask you, 3 half-lives have passed. How old is the fossil? After 3 half-lives, if each half-life is 150 days, that means that fossil is 450 days old. If it tells you there are only 4 atoms of the parent left, how many half-lives have passed? Here's 4 atoms of the parent. That's 4 half-lives. How long is 4 half-lives? 600 days. So we know that that sample is 600 days old. We'll practice these half-life problems in class, but this is what we can use to get the absolute age, the absolute date of fossils and rocks so that we know how old the Earth is. So that is the end of your notes for Unit 2, History of the Earth. Make sure you complete the document on Canvas and submit it when you are finished.